Think of a teenager who just finished their driving test with a perfect score. On paper, they appear to be a master of the road. However, that score doesn't predict how they will react to a sudden obstacle in their path, or how they will handle a passenger pressuring them to speed. Today, many companies are deploying artificial intelligence agents based on similar logic. They trust these models with financial and medical decisions because they achieved high average accuracy scores. In reality, relying on average accuracy is a significant risk for anyone deploying an autonomous system. A landmark study from the Mount Sinai Health System reveals the danger of this approach. Researchers tested an AI designed to provide medical advice using real-world scenarios. In one case, a patient arrived with acute respiratory failure. While the correct clinical action is an immediate ER visit, the AI recommended waiting 24 to 48 hours. This bell curve illustrates why these failures happen. Large language models excel at routine, textbook cases in the blue center, but performance drops dramatically in the extreme edge cases. Standard testing focuses only on the center, leaving developers unaware of edge failures. A high accuracy score acts as a mask, hiding these silent, catastrophic errors from the teams deploying the AI. Since we cannot predict exactly how an AI will reason, we must build a rigid architectural framework around it to ensure safety. Much like a learner's permit, this architecture begins with the idea that control must be earned over time, rather than granted immediately. The first stage is shadow mode, where the AI processes real scenarios in the background. Once it handles routine data, it moves to a human-in-the-loop workflow for review. Finally, proving reliability at extreme edges earns full autonomy without human oversight. Even a high-performing AI can suffer from disconnected logic. Disconnected logic is a failure mode where an AI's internal reasoning correctly identifies a risk, but its final action contradicts that logic. Because an AI's reasoning and its final output can operate as independent processes, the model is unable to reliably catch its own mistakes. This requires Layer 2, deterministic validation. This security layer uses external, rules-based engines to verify the AI's logic matches its output. If it detects a contradiction between reasoning and action, it immediately triggers a human escalation to prevent the error. Safety depends on having hard-coded rules that can overrule the AI's autonomous judgment when necessary. Sustaining this level of safety requires continuous monitoring, similar to reviewing dashcam footage after a new driver returns from a trip. Layer 3 uses a continuous flywheel approach, intentionally biased toward false positives, incorrectly flagging harmless interactions as danger. It also includes retroactive audits, which are manual reviews of interactions initially marked as passed, to catch any silent defects. In systems where safety is critical, it is much better to manage the inconvenience of a false alarm than to overlook a fatal error. Finally, we must protect against social anchoring. Social anchoring is a bias where an AI's clinical or professional judgment is swayed by the emotional tone or framing of a user. To find these hidden biases, we use factorial stress testing. Factorial stress testing is an evaluation technique that runs a single scenario through dozens of contextual variations to uncover breaking points. By stacking different social pressures or database failures onto a single task, we can measure if the AI's output shifts based on unstructured context. Our objective is to test for mathematical risk, not simply to see if the AI can provide a polite or well-phrased response. Safe driving requires a highly focused human operator, but it also heavily relies on seatbelts, traffic laws, and proper licensing. Deploying enterprise AI requires the same rigor. We must move past average accuracy, implement external validators, use shadow modes, and stress test for objective risk. Every AI agent has blind spots. The challenge for leaders is whether they identify them before their customers encounter them. Building this infrastructure is becoming a prerequisite for doing business. Organizations must find their system's weaknesses now, or be prepared to face the costs of failure on their own.